Quantum field theory, or QFT, is a theoretical framework in physics. It combines classical field theory, quantum mechanics, and special relativity. In simple terms, QFT describes how subatomic particles interact and behave. It is one of the most successful theories in physics. Imagine a field like a sea. Particles are like waves on this sea. QFT treats every particle as an excited state of its underlying field. This means particles are not seen as independent entities but as manifestations of fields. QFT is essential for understanding the fundamental forces of nature. It explains electromagnetism, weak nuclear force, and strong nuclear force. Without QFT, modern physics would be incomplete. The development of QFT began in the early 20th century. Scientists were trying to reconcile quantum mechanics with special relativity. Classical physics could not explain certain phenomena at the subatomic level. This led to the need for a new theory. The first breakthrough came with the work of Paul Dirac in 1927. He formulated the Dirac equation, which described the behavior of electrons. This was a significant step towards the development of QFT. During the 1940s and 1950s, QFT was further developed. Richard Feynman, Julian Schwinger, and Sin-Itiro Tomonaga made significant contributions. They introduced concepts like Feynman Diagrams and Renormalization. These tools helped solve problems in QFT. By the 1970s, QFT had become a well-established theory. It successfully explained the interactions of subatomic particles. Today, QFT is a cornerstone of modern physics. Quantum mechanics is the foundation of QFT. It describes the behavior of particles at the smallest scales. Unlike classical mechanics, quantum mechanics deals with probabilities. Particles do not have definite positions and velocities. Instead, they are described by wave functions. A wave function gives the probability of finding a particle in a particular state. The famous Schrödinger equation governs the evolution of wave functions. This equation is central to quantum mechanics. One key concept in quantum mechanics is superposition. A particle can exist in multiple states at once. This is different from classical physics, where a particle has a definite state. Another important concept is entanglement. Particles can become entangled, meaning their states are linked. Quantum mechanics also introduces the idea of quantization. Energy levels of particles are discrete, not continuous. This means particles can only exist in specific energy states. In physics, a field is a physical quantity assigned to every point in space and time. For example, the electromagnetic field describes electric and magnetic forces. Fields can be visualized as a grid filling space. Each point on the grid has a value representing the field strength. Quantization of fields is a key idea in QFT. It means that fields are made up of discrete units called quanta. These quanta are the particles we observe. For example, the electromagnetic field is quantized into photons. To understand quantization, think of a guitar string. When plucked, the string vibrates at specific frequencies. Similarly, fields can only vibrate at certain frequencies. These vibrations correspond to particles. Quantization solves many problems in classical field theory. It provides a framework for understanding particle interactions. Without quantization, fields would have infinite energy, which is not physically possible. Section 5. Virtual particles. Virtual particles are a fascinating concept in quantum field theory. They are particles that exist for a very short time. They cannot be directly observed but have real effects. Virtual particles are used to explain forces between particles. For example, the electromagnetic force between two electrons is mediated by virtual photons. These photons are exchanged between the electrons, causing them to repel each other. Virtual particles appear in the calculations of quantum field theory, but do not violate conservation laws. Virtual particles are a result of the uncertainty principle. This principle states that certain pairs of physical properties cannot be known simultaneously. For example, the more precisely we know a particle's position, the less precisely we know its momentum. Virtual particles allow for temporary violations of energy conservation. They borrow energy from the vacuum and then return it. This borrowing is allowed as long as it happens within a short time. Section 6. Feynman Diagrams. Feynman diagrams are a graphical representation of particle interactions. They were introduced by Richard Feynman in the 1940s. These diagrams make complex calculations in quantum field theory easier to visualize and understand. A Feynman diagram consists of lines representing particles. Straight lines represent fermions, such as electrons. Wavy or dashed lines represent bosons, such as photons. The points where lines meet are called vertices and represent interactions. Each element of a Feynman diagram corresponds to a mathematical expression. By drawing the diagram, physicists can write down the corresponding equations. This simplifies the process of calculating probabilities of different interactions. Feynman diagrams have become an essential tool in particle physics. They provide a clear and intuitive way to understand particle interactions. Without them, many calculations would be much more difficult. Section 7. Renormalization. Renormalization is a process used to deal with infinities in quantum field theory. When calculating interactions, physicists often encounter infinite values. These infinities arise from the contributions of virtual particles. Renormalization removes these infinities by redefining certain quantities. For example, the mass and charge of a particle are redefined to absorb the infinities. This makes the theory finite and physically meaningful. The process of renormalization was developed in the 1940s and 50s. Richard Feynman, Julian Schwinger, and Sin-Itiro Tomonaga played key roles. Their work showed that quantum field theory could be made consistent and predictive. Renormalization has been essential for the success of quantum field theory. It allows physicists to make accurate predictions about particle interactions. Without it, quantum field theory would not be a viable theory. Section 8. Quantum Electrodynamics, or QED. Quantum electrodynamics is a specific quantum field theory that describes the interaction of light and matter. It deals with the electromagnetic force, which is one of the four fundamental forces of nature. QED is one of the most accurate theories in physics. In QED, particles like electrons and positrons interact by exchanging photons. These photons are the quanta of the electromagnetic field. The theory uses Feynman diagrams to calculate interaction probabilities. QED has been tested to an extraordinary degree of precision. Experimental results match theoretical predictions to many decimal places. This makes QED one of the most successful theories in the history of science. The development of QED was a major milestone in physics. It showed that quantum field theory could be used to describe real physical phenomena. Today, QED is a fundamental part of our understanding of the universe. Section 9. Quantum Chromodynamics, or QCD. Quantum chromodynamics is another quantum field theory that describes the strong nuclear force. This force binds quarks together to form protons and neutrons. QCD is essential for understanding the structure of atomic nuclei. In QCD, quarks interact by exchanging particles called gluons. Gluons are the quanta of the strong force field. Unlike photons, gluons themselves carry the force they mediate. This makes QCD more complex than QED. QCD uses a concept called color charge. Quarks come in three colors: red, green, and blue. Gluons carry a combination of these colors. The force between quarks gets stronger as they move apart. This is known as confinement. QCD has been successful in explaining many phenomena in particle physics. It is a crucial part of the Standard Model, the theory that describes all known particles and forces. Without QCD, our understanding of atomic nuclei would be incomplete. Section 10. Practical applications of quantum field theory. Quantum field theory is not just a theoretical framework. It has practical applications in various fields. One of the most significant is in particle physics. QFT is used to predict the outcomes of particle collisions in accelerators like the Large Hadron Collider, or LHC. QFT also plays a role in condensed matter physics. It helps explain the behavior of electrons in solids. This has led to the development of technologies like semiconductors and superconductors. Another application is in quantum computing. QFT provides the theoretical foundation for understanding quantum bits, or qubits. These are the building blocks of quantum computers, which have the potential to revolutionize computing. QFT is also used in cosmology. It helps explain the behavior of the early universe and the formation of structures like galaxies. Without QFT, many aspects of modern technology and our understanding of the universe would not be possible. Section 11. The importance and impact of quantum field theory. Quantum field theory has had a profound impact on physics. It has provided a deeper understanding of the fundamental forces of nature. QFT has unified quantum mechanics and special relativity, two of the most important theories in physics. QFT has also led to numerous technological advancements. From particle accelerators to quantum computers, QFT has been instrumental. It has also enhanced our understanding of the universe from the smallest particles to the largest structures. The importance of QFT cannot be overstated. It is a cornerstone of modern physics and a testament to human ingenuity. As we continue to explore the universe, QFT will remain an essential tool. In conclusion, quantum field theory is a remarkable achievement. It has transformed our understanding of the universe and paved the way for future discoveries. By mastering QFT, we can unlock the mysteries of the cosmos.